Hi, the Monty Hall problem. Have you heard of it? When it first appeared in the 70s, its solution provided great controversy. It divided many mathematicians, some of whom still believe that its solution is invalid. Let's see if you agree with that. The Monty Hall problem. This is a well-known problem that first developed in the 70s, and it's based in the area of probability. Very loosely, the idea developed from the American quiz show Let's Make a Deal, which was hosted by Monty Hall, hence the name after which it was named. Marilyn Vos Savant, who was a well-known American columnist at the time and also a famous mathematician and scientist, was asked a question about the problem by a reader. Her answer created much controversy because it defied all the thinking of famous mathematicians at the time. They disagreed strongly with her solution and put her down in many different ways. So the best thing is, let's have a look at the game and the proposed solution and see if we agree or not with its validity. Now basically, in Let's Make a Deal, a contestant was given a choice of 3 doors to choose from. There they are. Behind one of the doors was a good prize, namely a car, and behind the other 2 doors were booby prizes, let's say a goat. So what the contestant had to do first was to choose one of the 3 doors, let's say in this case door number 3, and he or she was not told what was behind the door at this stage. The host, Monty Hall, would then reveal what was behind one of the other 2 doors, let's say door number 2, which is a goat. Now the important thing at this stage is to know that the host knew all along what was behind all 3 doors. That is vital. The contestant was then asked whether or not he or she would want to swap their choice of door number 3 with door number 1, the other remaining door. What would you do? Would it make any difference? In this situation, swapping would have been beneficial because the car was behind door number 1. Are you any better or worse off by swapping or not swapping? That is the crux of the problem, and we will look at that in detail. Should you swap doors? Okay, let's look at what's going on in detail. The brief answer to the question, should you swap doors? Yes, always swap, no exceptions. Why? Let's see. Here there are 3 doors. Now, all things being equal to begin with, there is a 1 in 3 chance that the car is behind any one of those 3 doors. In other words, PR, the probability of a car behind any of the doors, is 1/3. So the contestant has chosen door number 3 and the host has revealed a goat behind door number 2. So we know the probability of a car in door number 3 is 1/3. The question is the probability that the car is in door number 1, the unopened door, also 1/3? Or, as some people would think, is the probability that the car is now behind door number 1 1/2, because there are 2 doors that are unopened, and therefore the chance behind each door of a car is 1/2. So do you think it's 1/3? Do you think it's 1/2? Or do you think it's something else? In fact, the answer is something else. The probability that the car is in door 1 is neither 1/3 nor 1/2, it's actually 2/3. Can you figure out why? This is the basis of the controversy back in the 70s. Almost everyone refused to accept that you have a better chance of swapping doors because you have increased your probability 2-fold. Can we explain why that happens? One way of looking at it is by looking at a similar picture on a larger scale. Now let's suppose we have 100 doors. Obviously a much larger situation than the game. And let's suppose the player has chosen door number 1. Therefore we can say that the chance, the probability that the car is in door number 1, or that the car is behind door number 1, is 1 in 100. Now out of the 99 doors remaining, the host has revealed 98 of them, and each of those 98 doors has a goat behind them. keep in mind that the host knows what was behind every door. Your decision is, would you now swap door number 1 for door number 100? Have you got a better chance of getting the car? Do you still think it's a half or 1 out of 100? Well, as we said earlier, you're always better off swapping. Now, the probability of a car behind door number 1 is 1 in 100. We know that. The probability of a car in door 100 is now not 1 out of 100, but 1 plus all of the doors that were revealed, the 98 doors. So the total probability that the car is behind door 100 is now 1 plus 98, which is 99 out of 100. Can you appreciate why? Basically, the hosts, knowing what they know, have deliberately chosen to reveal most of the goats, thus eliminating that part of the probability that would have given you less of a chance. And that part that has been revealed is now added to the probability of having the car. In other words, it has increased your chances by removing the component of the probability attributed to getting a goat. Still confusing? Do you think statistics lie? There is one conclusive method which we can apply that would demonstrate what's going on, and that is to perform a simulation. And the simulation will be that it doesn't matter how many doors we start with, the probability of getting the first prize, the car, is increased significantly by swapping. And the fractions are 2/3 to 1/3, and the probabilities are 2/3 to 1/3 in favour of swapping. Or as a percentage, about 67% to 33%. Let's see the simulation in action. Let's look at how the simulation works. Here we have our 3 doors. Let's suppose the contestant chooses door 1 as thinking that there's a car behind it. The host, knowing where the car is, reveals what's behind door 3, a goat. Should the contestant swap door 1 for door 2? At this stage you might think it makes no difference. It's a 50-50 proposition. But let's reveal what's behind door 2. It was another goat. If the contestant had stuck with door 1, they would have won the car. If they had swapped, they would have lost. And that's what's shown underneath. Trial number 1, if they had swapped, 0% gain and 100% by not swapping. Let's try another trial. Door number 1 again, chosen by the contestant. And this time, the contestant would have been better off swapping. Another trial. Notice what's happening with the percentages at the bottom. There's trial 4. At the moment, we have at the bottom that the contestant would be better off 75% of the time if they swap. And the 5th trial, 80% by swapping. Let's speed up the process. Up to the 99th trial, we'll go to 100 trials. So what have we got now? After 100 trials, 68% of the time the contestant would be better off by swapping their first choice for the door that remains unopened. Let's continue and do a lot more trials. Up to 1,000 trials now, and we have about 67.1% in favour of swapping, and that fraction is about 2/3, isn't it? Now let's move on to a lot more trials. Let's try 1,000,000. We're getting close to 100,000 trials, and you can see there that the chance of having a car by swapping is about 66.7%, or 2/3. Let's see what happens when we get to 1,000,000 trials. Close to 500,000 trials, and you can see that the percentage for swapping is 66.67, which is pretty much spot on to the expected 2/3. Let's see how we go with 1 million trials. We're almost up to 1 million trials. The percentage is 66.64. Let's have a look. There we go. So what can we conclude? Well, the percentage, 66.64, is pretty much 2/3, so we can say that you should swap when you have the opportunity to do so, and that 2/3 of the time you'd be better off. Until next time, bye bye.